Welcome back to another lab session. Today we are going to see manipulation of light intensity and polarization. So as shared in the lab manual, we have three objectives for today's lab. First would be verification of Malus law. Second would be changing the polarization of input beam using a bifringent material, and then seeing the bifringence property of some plastic materials. According to Malus law, if a polarizer, I have a seed polarizer with me here. So if a polarizer is placed in the path of a incoming linearly polarized light, then the transmitted light will have the intensity given by I cos square theta, where I is the intensity of the incoming beam, theta is the angle between the polarization of the incoming beam and the path axis of the sheet polarizer. So if the path axis of this sheet polarizer is changed, so this angle keeps on changing, so the intensity on the other side will keep on varying. So that's what we will try to see using our setup today. And secondly, what we'll do is, in the path we'll place some bifringent material which will change the polarization. So even due to that material, we'll see the change in intensity. Even if this angle is kept fixed and there is something in between which changes the polarization angle of the incoming beam, then we'll see a change in intensity, because again something has changed the polarization angle and then made a net angle between the incoming beam and polarization sheet. So in the second part, we'll see the working of quarter wave plate and half wave plate. Both has been explained in class, so we'll just see the same thing in action here. And in the third part will be just an observation of bifringent property in some plastic material, where due to plasticity there is some residual stress developed in the material, and that stress results into some bifringence property being shown by common plastics like scale and anything common. So here we have everything that we need for the Malus law experiment. So I have two polarizers, the optical stand, laser with a laser mount, and laser driver unit, and I have pinhole detector and pinhole detector measurement unit. So I'll set up everything and we can start the experiment. So here we have set up for the Malus law experiment. So I have a light source, which is a linearly polarized light source driven by a laser driver. Then I have a pinhole detector to measure the intensity of the laser beam, and pinhole detector gives the reading in currents which is proportional to the laser intensity, and the scale can be adjusted to either microampere or milliampere as needed. And then I have a polarizer here whose path axis I can just change using this setup. So you can see, as I am changing the path axis angle of this polarizer, there is a change in current signifying the change in intensity of the transmitted laser beam. Okay, but so actually this laser source is not a perfectly linearly polarized light source. So as to make it a linearly polarized light source, I will place one more polarizer in between. So now I have placed one more polarizer in between, and then I will just try to, so now this light I can assume as a perfectly linearly polarized light, and then I can adjust the angle of this polarizer to get the maximum here first. So now I can place my analyzer. It's the second polarizer, I will call it as analyzer. So you can see as I am changing the path axis of the polarized analyzer, you can see the change in intensity of the laser beam. So now if you plot this angle of this polarizer versus the current, you will get a cos square fit for the data, and so that will be the verification of Malus law. So in the table here on the screen, we will present you the data recorded. So you can see the data and the corresponding plot, and it shows the cos square variation of the transmitted intensity of light. Okay. So now we will move on to the next experiment, that is characterizing half wave plate and quarter wave plate. So, okay. So to do that, we have this general setup where we have the very same setup that we use for Malus law. Only difference here is the analyzer is kept at cross angle to the polarizer. So due to which the output intensity will fall to 0. So I'll just adjust the polarizer angle to make the output intensity fall to 0. So you can already see that the output intensity is in microohms. So I'll further rotate the analyzer till it goes to 0. Okay. So this is the minimum that I got. So this is the general analyzer polarizer setup, okay, which is used to analyze any material which just changes the polarization of a beam, because right now this analyzer polarizer angle has been set to cross angle so that the output intensity is minimum. But if you place anything which changes the polarization, just that interferes with the polarization here, that will result in some intensity at the output, and the intensity change will be proportional to the polarization change produced by that material. What is it? A rotating frame, right? Okay. So this is the half wave plate with me, and it has a fast axis marked onto it, and I can change the fast axis by rotating the rotating frame. So now if this fast axis is kept at some angle theta to the polarizer angle, so as explained in class, the half wave plate rotates the polarization of the incoming beam by 2 theta. So the same effect we will observe here using the cross analyzer polarizer setup. So now I have placed the half wave plate in between the cross analyzer polarizer setup, and I have placed such that the fast axis of this half wave plate is along the polarization of the incoming beam light. So you can see that there is no rotation, because if it is at 0 degree, it is not rotated, and that is why the current is still at the minimum. So now if I place a fast axis at some angle theta to the polarization of the input beam, the output beam will have the polarization rotated by twice that fixed angle compared to the input beam. So now if I rotate the half wave plate by some angle theta, say 20 degree, so I'll start the rotation here. So from here I'll just rotate it. So if I rotate it by 20 degree, so you can see that the current here at the detector has increased, and so this is because the half wave plate has brought about the rotation of the input beam by 40 degree, because it was kept at 20 degree to the polarization of the input beam. So it has rotated the input beam by overall 40 degree, and we can verify the same by rotating the analyzer by 40 degree to get back the minimum intensity. Here we will rotate the analyzer till we get a minimum back over there. So I will start rotating. So you can see that reading right now is in some milliamps. So I will start the rotation. So you can see that there is a minimum somewhere around here at 16.8. Okay. So any further above that is increasing that side as well as increasing that side. So somewhere here there is a minimum here 16.8. So now we can see the reading here. So it is reading 140 degree. So you can see that the total angle by which I rotate the polarizer is from 180 to 140 degree. So it is 40 degree. So this is how this shows that the half wave plate has rotated the input beam by 40 degree when its fast axis was kept at 20 degree to the input beam. So this concludes the half wave plate characterization. So now we will move on to the quarter wave plate. So we will replace the half wave plate in the setup by a quarter wave plate. So here also fast axis is marked. So we will do the same experiment here. So what we will do here in this case is we will keep the quarter wave plate at 45 degree to the polarization of the input beam. We will keep the fast axis at 45 degree to the polarization of the input beam. So this will result in the circular polarized light, and now circular polarized light once analyzed through analyzer should give us the constant current for all the angles as explained in the class already explained in the class. Okay. So now I have placed the quarter wave plate in between the cross analyzer polarizer setup, and I have placed it in such a way that the fast axis of this quarter wave plate is aligned with the polarization of the input beam. That is why you can see that the intensity is still maintained, it is at the minimum right now, 0, 0. So now the quarter wave plate is placed at 0 degree. So from here if I rotate the quarter wave plate by 45 degree, so I have rotated the quarter wave plate by 45 degree. Once I rotate the quarter wave plate by 45 degree, to make the fast axis of a quarter wave plate to be at 45 degree to the polarization of the input beam, the output of the quarter wave plate is going to be a circularly polarized light. Okay. So now the output of the analyzer is constant irrespective of the angle of the analyzer. So you can see that I am rotating the analyzer here, but the current is very much constant here. So the fluctuation is to 4.95 from 4.4, 4.6. So from 4.0 to 5.0. So after a 360 degree of rotation, you can see that there is very little fluctuation in the current. So you can say that the beam here is circularly polarized, and that was due to the quarter wave plates, and that explains the working of the quarter wave plate. So now the third part of this today's lab session would be to demonstrate photoelasticity in different dielectric materials. So photoelasticity is a property shown by some of the materials under stress where they start showing bifringence. So I have a plastic spoon which during the manufacturing process will develop some residual stress, and that points to all those points will show some bifringence, show the bifringence of light. So if I put this in the if I put this spoon in the laser beam path, you can see that there will be a spike in current due to the bifringence shown by the plastic. You can see as I move it, the current will changing because of the different stress at different point. So it's showing different bifringence at different point. So similarly, I have many different materials, plus different plastic dielectric materials. I have a glass, I have a cubit, I have fork. So, so in this way we can actually take an image of stress pattern inside a dielectric material. So one easy way of that would be, just instead of the laser source, we can use a monitor as a source of linearly polarized light. So, or it can be a mobile screen also if it has OLED screen. So that will also be a source of linearly polarized light. For analyzer, you can use a polarizing sheet as an analyzer. You can place it at a cross angle to the polarization of the light coming from the screen. For a pinhole detector, you can use another mobile phone camera to take a picture of the stress pattern. So this is a setup. So in this setup, now if you introduce anything in between, any plastic dielectric material which shows photoelasticity, and you just take a photo from your mobile phone, you will see the stress pattern inside the plastic. So image shown here on the screen actually shows one of the image taken in very this similar way, and you can clearly see the stress pattern inside the plastic. So there are some of the few images shown here on the screen for glasses for different color of screen, and you can see the stress pattern inside. So the point on the screen which is in bright is actually the point on the plastic where there's a large residual stress, and wherever it is almost white, it's like there's no residual stress at that point. So you can use this phenomena to find the stress pattern in any transparent dielectric material. So here on the screen, Malus law plot has been shown. So here what we have done is we have recorded the intensity, output intensity of the laser beam at different angle at different analyzer angle. So you can see that this fits to the cos square curve. So this verifies the Malus law. And then moving on to the half-wave plate, you can see the plot for half-wave plate. So you can see when the half-wave plate was rotated by 20 degree, you can see that cos square curves shift by 40 degree, and if it is rotated by 45 degree, this plot shifts by 90 degree compared to the original Malus law plot. Then for the quarter wave plate, you can see that the intensity remains for the quarter wave plate. You can see that the output intensity remains almost constant for the different angle of analyzer. So that concludes the today's session. Thank you for being with us.